Okay, hopefully this will be a fun one. So this is about hashing in an application called Heavy Hitters. So last time we did some of this, or last two times, we did some intro to probability and a few applications to get us started. Things like randomizing 3-sat and then randomly solving 3-sat or approximating and then de-randomizing that, as well as um, this randomized divide and conquer and quicksort. And I know that some people had their presentation cut off, but the rest of the details are in the notes, so hopefully that's legible. Um, and that was just this part where we went from an expected running time to a high probability running time. I'll also put up the recorded video probably this weekend too, so you can catch the last few. Which is mostly me complaining about everyone being kicked out of the class, and then also doing a little bit about the proof. Okay, um, so that's where we were last time. So today will be about this frequency estimation problem, and it'll be something that occurs in something called the streaming model, so that'll also be new. And then, kind of more technically, will be our first exposure to hash functions, and we'll be using Markov's inequality again. So that's today's plan. So, okay, have have you all been to this website before? I actually recently checked. It doesn't quite look like this anymore. This was it a year and a half ago. So this is Google Trends, and they keep track of what are the things that people are querying the most. And so as of, well, maybe you guys can guess when this was based on the trends when I snapshot this. So at some point in time, that movie "Don't Worry, Darling" was trending, along with I guess there was some kind of soccer game with Barcelona, and I think Chet Holmgren had just gotten injured for anyone following basketball at the time, and I think Nick Cannon had his like 1,000th child or something. Um, yeah, so they're tracking all these things, and they're not just tracking this for sake of curiosity. They want to cache all the queries, right? So like just about everything out there, 99.999% of you are asking the exact same thing all the time. Okay? So it seems like, wow, they sure found that answer on the internet really quickly. It's because they didn't look at the whole internet. They already did that. And they already knew you were going to ask the question. Okay? So they might put in a little effort into finding similar queries and things like this. But there's a lot of caching going on, right? But the interesting question is how, right? Clearly, like any combination of English words is possible. There's way too many different queries to maintain a counter for each one, even with Google's data centers, right? So this is sort of an interesting challenge. So we're going to model this problem as follows. So we're looking at a setting where the input really doesn't fit on a computer, right? You're Google, you're looking at every single query to ever come in. So we're going to imagine this sort of coming in some kind of input stream, okay, like a read once stream that's just coming through your computer, and elements will appear one at a time. So maybe the first one is the letter A. I'm just using letters. Okay, so the letter A comes. Okay, I've seen the letter A once. The next one, letter B. I've seen letter B once, right? And so these elements come in one at a time, and your computer is keeping track. Okay. Now, okay, so that's simple, and our goal is to identify all the queries that are mildly popular. So, for example, it could be 5%, it could be 1%. For Google, it's probably like 1/1,000,000% or something. Okay. And I just want to maintain a list that includes all these elements. Okay, maybe those are the ones I'll cache. Okay, so what makes this interesting is I imagine imagine this square was like the computer, and it's kind of going through the stream. Okay. Now you want to think of the computer's memory as being much, much smaller than the input size, which is probably unlike any problem you've seen before in a normal algorithms class. Okay? So this algorithm needs to go through and needs to decide what it wants to remember, and it's going to have to leave some information out, probably. Okay? So our goal is to identify all the heavy hitters with what's called sublinear space, so sublinear in the input size. Okay? So, what does that entail? The point is that if I try to save all the counts in a dictionary, it's going to take too much space. In fact, we can even get a lower bound on, okay, let's ask this. Suppose I had, so the total stream had length m, and the number of items, the number of different items, the different labels, was like n. And suppose I wanted to maintain all the counters exactly. What's a lower bound on the amount of space I need? The function of m and n. Sorry? Okay, m log n. Why? Oh, okay. Or maybe n log m. Sorry. As usual, we choose the only two letters that look and sound the same. Well, okay. If you actually maintain a counter for each one, that would take n log m. Right? A number can be between 1 and m. And there's n of them. But how do we know there's not anything more clever we can do? There's some way to compress it. I want to argue it's hard to compress. But I wanted to maintain things exactly. Okay. I mean, that's correct, but surely is not a proof. Surely is what we're trying to prove, right? Well, it's hard because you want to rule out any compression argument, right? So it's not enough to fix one and say, that couldn't work. Well, so these counters come in, right? And there's some kind of outcome, which is a bunch of different values. How many different possible outcomes are there? So one outcome will kind of consist of that full set of counters. So how many possibilities are there? Yeah. Oh. Yeah, so the number very precisely would be like m plus n, choose n, or maybe m plus n minus 1. But basically, out of the m, right, some of them will be assigned to the first one, some of the appearances will be assigned to the second, some of the appearance will be assigned to the third. Okay, where does this quantity come up, m plus n minus 1, if you've taken a combinatorics class, this is often come up, is I imagine this kind of dots and bars, but you can imagine like n plus n minus 1 total slots, okay? And then I'm going to put n minus 1 dividers. There's a divider, there's a divider, there's a divider. Okay, so I choose n minus 1 things, and I say, oh, how many slots was before the first divider? That'll be my first counter. And then the next gap is how many is assigned to the second counter, right? So this is the number of ways to divide up m among n if you're not worried about which one goes to which, just so it sums up to m. Okay. And if you take the log, oh, okay. Okay, so that's the number of different ways, right? And now you know that your computer, right, if it has k bits, it can only output 2 to the k different things, right? It's because only 2 to the k different strings. So that tells you that you need at least log of n plus n minus 1, choose n. Okay? So that's going to be like, oh, n plus n minus 1 times n plus n minus 2, and so forth. Okay? And then you'll get this n log m if you just kind of go a little bit more slowly than I did working with the quantities. Okay? So anyway, not only do we not want to save all the counts in the dictionary in general, but you shouldn't really expect to be able to do things exactly. Okay, so, right. What I want to do is something more like square root n or log n space. And I'll just treat all the elements as IDs between 1 and n. Okay, so, as we pointed out, it is actually already kind of impossible to do this, right? We just showed, okay, you actually need like a n log m space just from this simple counting argument. So how or why then? Okay, what I'm asking is, if it's literally impossible to count everything exactly, then why might there be any kind of hope? Yeah. Yeah, we can allow for margin of error. Um, so if uh, that's right. So you only need the exact counts if you really want exact solutions in some sense. But if I wanted to do things approximately, just like with SAT, then maybe things are a little bit easier. Okay? There's also one more hint. So suppose I wanted, or one more hope. Now suppose I only wanted the 5% heavy hitters. Okay? How many 5% heavy hitters are there? At most 20. At most 20. Because each occupies 5%, and at some point it adds up to 100%. Right? So the fact that the output that we're going for is small is also some amount of hope. Okay, so between approximation and the fact that we only want the heavy hitters, okay, and we'll also allow for both approximation error, and we'll also do some randomization. Maybe it's not right all the time, but it's right most of the time or something, right? But these are all relaxing things that are saying, oh, okay, you don't need to get all the heavy hitters perfectly, or in some sense, we have to figure out how to relax it. And if I allow some randomization, allow some approximation, and besides, there's not even that many heavy hitters out there. Okay, now there's at least some hope that even if I can't count everything exactly, I can still identify the heaviest counts with this very small amount of space. Okay, so that's the fun of it. All right, so here we have to take a quick pause, and I have to give you some tools so that you can solve this problem. So I'm going to introduce hash functions and remind us again about Markov's inequality, which we used last time. Oh, I guess Markov's inequality comes first. So just to briefly remind us, so if x is some non-negative random variable, we're just saying how often can it greatly exceed the average. The simplest one I always think of is something can only exceed the average at most half the time. Otherwise the average would be bigger, but that's a contradiction. Okay, but that applies for like any value. Like how often can something be 4 times bigger than the average? At most 1/4, right? Or 1.1 times the average. Like 90%ish or something, right? 1 over 1.1 and things like this. And this is just because, oh, things have to add up. So nothing special. Somehow Markov got it named after him, which is really the coup. And the key point is that even though it's so simple and it's just this very elementary argument, the really great part is you don't have to assume anything about x. We'll have much fancier inequalities later in the class, but they often make much stronger assumptions about x. Like maybe they're roughly the sum of coin tosses or something like this. The fact that X may be modeling a bunch of interconnected things and you can just ignore it. That's one reason why this is so effective. Okay, next are hash functions, which you have probably seen in some form before. So usually we hash down. So you have some large input space, I think of like n different items, and you want to slot them into k smaller ones. Okay. So usually, n is the bigger one, k is the smaller. There's some other situations, but today that'll be the case. And they're going to be hashing down to something small. Okay. And in most applications, well, you might, yeah. So, okay, let's see what's here. So, as you might know from something like a hash table, which we'll study in depth and do a hardcore one next time, you might have only some of these slots occupied, and then when you hash them down, you want to place them into a smaller array on your computer. Okay, and you're hoping that maybe this will be red and this will be yellow, and you're kind of hoping they go to different spots. Okay, so you can kind of take something with lots of holes and sort of fill in the holes. Okay, and the high level strategy is to try to do it randomly so there's no kind of bias. Regardless of the input, you're hoping that the collisions are just what some randomness would give you, and then you're hoping you can just analyze and understand and mitigate the accidental, the natural random error. Okay. But you get good worst case bounds because the adversary doesn't know your randomness. Okay, so no matter how they place it, you'll generate a random function that, you can't scheme against. So the ideal version, the best possible, I don't know, the nicest one from an analytical point of view is uniformly random. Okay? So a uniformly random hash function just takes every number between 1 and n and gives it a completely random number between 1 and k, irregardless of the other ones. So then you can start saying like, oh, what are the odds that 4 of these items collide? And it's completely independent. Oh, this one has to go there, and the next one has to go there, and the next one has to go there, and the next one has to go there. And that's 1 over k to the 4th. Okay, or you fix the first one, and then you need 1 over k, 1 over k, 1 over k kind of chance. That's 1 over k cubed. Okay, but it makes it easier to reason when those assignments are completely independent of one another. So that's the easiest thing. And sometimes when you're making algorithms, it's helpful just to imagine you have access to this. But there is a shortcoming. There's something a little impractical about ideal hash functions. Anyone have? Yeah. Oh, some of the slots might go empty. That's a good point. But, well, I guess we'll get better at analyzing this. But if you have n where n is much bigger than k, it will be quite unusual for one slot to be completely empty, because it'll be completely, as n gets bigger compared to k, if I'm looking at the perspective of one of the smaller slots, there's so much randomness coming in, you'd have to get really, really, really unlucky. It's going to be pretty well behaved. More randomness in this class is actually good. So it is true that you could get extremely unlucky, but I think you'll find the behavior, again, when we do more calculations, I'll be able to make this more precise, to be relatively stable and manageable. Actually, so the issue is not spreading the elements. From our new perspective as randomized algorithms people, complete randomness is like perfect. Yeah. Yeah. Okay, so maybe I should be more careful. So when we talk about these random functions, in this case, this hash function does not flip a coin each time it's called. We actually will, randomly create an entire function ahead of time and then use it. So that's not precisely the issue, but that's actually a good point. So, like, how would you generate and write down an ideal hash function? Yeah. Yeah, maybe it's hard to do, but let's say even if you did, right? So for each number, you sample one thing and you like write it down, right? Well, when n goes to k is k smaller, there's never going to be a clean inverse. There's always a pigeonhole principle. Yeah. Yeah, so imagine, you can generate the function by sampling all n, uniformly random. And maybe there's other ways to do it too, but I don't quite see it. But then you'd have to like write down the numbers, right? Because there's no patterns, there's no structure. I don't see how you could compress it, right? But we can make this more formal. How can we prove that an ideal, something that generates ideal hash functions requires some kind of very long description length? Yeah, okay, so if I was sort of if my family of hash functions was this ideal hash function family, then I can output any function from n to k, right? Now, how many functions from n to k are there? Yeah. All right, there's k to the n. And if I have L bits, how many hash functions can I describe? 2 to the L. So that tells me that the log of however much, oh, sorry, the space I need, okay, that's not an eraser. That's a yellow thing. Okay. Um, so 2 to the space in bits has to be at least k to the n, right? We take the log of both sides. Space has to be at least n log k, which is how much space it would have taken if I had just written down everything, right? So in fact, you can't really do any better than this, just again from a simple counting argument. So an ideal hash function is actually great. We haven't done enough calculations together for me to convince you that the more random, the better. The real issue is that, oh, space is an issue, especially in the streaming setting where I'm actually quite concerned about space. This is impractical. So, okay. So here then is so what happens then is we start looking at things that are kind of look random, but they're a lot more limited. But we're very precise about what we mean about limited. It may still be random enough to be useful. Okay, so this may be the simplest or the most minimal hash function that's still useful or definition of something. Okay, so it's called a universal hash function. Not really sure why it's called a universal hash function, but okay, so it's a mapping from n to k just like before, but it doesn't even guarantee that any particular item can go anywhere uniformly at random. All it guarantees is that for any two input items, the odds of them colliding are as if they were uniformly random, which is 1 over k, right? Because the first item goes somewhere and the second item can go anywhere. Kind of intuition. But only up to two items. It doesn't tell you anything about three or four or anything like this. Okay? So all it does is say the odds of any two given items colliding is at most 1 over k. That's the only guarantee you get. Okay? So it's much weaker than an ideal hash function, although there's still some randomness to it. But this can actually be done much simpler. Right. So, okay. So something like this. I take x and I do ax plus b mod a prime mod k. So let me expand out these parameters. So p is some large prime number, and there's a homework problem that forces you to kind of do this and go through it. But p needs to be a prime number bigger than k for this analysis to go through. A and b are totally random. Okay, a is not zero because zero will give you some issues. Okay, so but you're really just doing ax plus b where a and b are totally random. You do it modulo a prime, a large prime. And then you do mod k, so you hash it back down into the k slots. Or hash is the wrong word, you project it back down into the k slots. Okay? So of course this is a very simple function. Very simple to program. It'll be really fast on your computer. It's nothing weird. It takes very little space, right? Just like two numbers. the logarithmic space. Three numbers, I guess, including the prime. Okay. Um, but as you'll show in the homework, this will give you your universal hash guarantee. Okay, so what I'll focus on is just trying to use this so that, because the homework's a bit tedious, it'll excite you to go through the calculations. Okay, so let's go back to the fun problem. Okay, just reminding us we're doing this heavy hitters and streams. Okay, items are coming in. I want to identify everything that's, I don't know, occurs at least 1/20th of the time or something. And the goal is to somehow do this in sublinear space, right? Which on one hand would at first seem impossible, but we're going to try to take care of advantage of some approximations. And I'm going to generalize 5% a little bit. I'll call it epsilon heavy hitters. So that's saying, instead of epsilon being 0.05 for 5%, it'll be, something that occurs at least an epsilon fraction of the time, where epsilon is some value between 0 and 1. Okay. Good. And sometimes it's helpful to focus on this very closely related problem of frequency estimation. So there's two vocab words here: total frequency or absolute frequency is the exact tally, and then relative frequency is that fraction, divided by the length of the stream. Okay, so 5% means the relative frequency is at least 0.05. Okay, so that's pretty straightforward. So, okay. So we want to estimate all of the relative frequency up to epsilon additive error. There's not enough space for all the counters. Okay, and as we've already discussed, then we're going to have to relax this a little bit so that we can do something useful. Right? So, I should have mentioned this. Okay. So, I should have gave this as a puzzle, but it's too late now. Okay. So again, I've shifted from the heavy hitter problem to the relative frequency problem, which is pretty similar. If I get the relative frequency of the heavy hitters. But now it does look like I need to maintain counters to get relative frequencies, right? But lucky for us, and I wish I had asked it to you all, 0 is a good counter for almost all of the elements, right? So if I'm allowed 5% relative error, then 0 is good for all but 20 of the elements. Okay, so that's great news. So at some level, you could actually maintain counters for all the heavy hitters, except for what? Yeah. You don't know which ones are the heavy hitters. You only see the sequence once, and you can't repeat. The Google search has come and gone. You don't want to remember what they're squaring. Yeah. Okay. Um, okay. What else is here? Okay. All right. So I wanted to take the moment to give you all a chance to try to think of some algorithmic ideas. That was one suggestion, try to sample or something. But that feels like two passes, right? But this is an interesting puzzle, right? Okay. You want to count at most 20 elements or something. They're the 20 biggest ones. You don't know which ones are going to turn out to be the biggest. And the adversary gets to control the stream, right? It can load up the beginning with elements that look big, but once you see the rest of the stream, we're in fact quite insignificant. Stuff like this, right? So it's just fun ideas. It helps appreciate the problem to think of ideas. Okay, so you said hashing. We are going to use hashing, or else I wouldn't have introduced it. Hash something down to a small space. You hash all the items down to a smaller space. Okay, so we're gonna hash, well, like what would the algorithm actually be, right? So okay, we have a hash function. You have hash functions. But more concretely, what would you do? Yeah. Okay, let me try my best to recap. So it's like, oh, can we like take small bites off that fit in memory? I look at some small portion and say, oh, these appear to be the heaviest in the first part, and then like those are kind of like candidates for the counters in the next one. So one point where you don't get randomness is we don't control the order of the stream. This might work better if I was promised that the elements were completely scrambled uniformly at random, because then some chunk would be kind of like the frequency, the histogram might be representative of the whole histogram. But, they might be adversarially set up against you. It's possible, for example, that the heavy hitters just barely occur in each of the windows, but in any single window never look that great. Yeah. So, but that is a reasonable, yeah. Any other? Yeah. Okay, so just help me flesh it out a little bit. So you have a hash function going from like all the possible elements to something smaller. And then for each of these k smaller slots, you would have a. Okay, so at some level, it's almost like taking, oh, here's the n counters I want to maintain exactly, right? But I can't. So let me try hashing them down, and these will be like sums of original counters. Okay, that's a reasonable idea. At least there's a small number of counters. Okay. And what is some of the intuition behind this? You're hoping you don't have two heavy hitters colliding, yes. Although one thing to worry about, let's say a heavy hitter goes to a particular counter, so that's good, and maybe no other heavy hitters collide with it because you got lucky. But there's still a lot of other elements contributing noise, right? So that's, well, maybe we should be careful about the word uniformly because what we have is this universal hash function in particular. So not exactly uniformly because that would be more like a uniform hash function. You can control k, yeah. The bigger the k, the more space your algorithm will use. Okay, so, right, so keeping in mind that we can estimate up to epsilon additive error, okay, let's do exactly this. So I think I've drawn the picture down here. I just have to erase things. So we're going to allocate some smaller array of counters. Okay, so I've done 10 over epsilon, and we'll see why that's a good choice as we do some calculations. And and we'll allocate those counters, and we'll hash the element I to the corresponding counter. Okay, so every time like I see an element like this one goes up by one, and then this counter will go up by one, kind of thing, right? And And so some counter down at the bottom is going to represent the sum of all the frequencies of all the elements that hash in. Okay, so that's a simple algorithm, I think. Okay, good. Sorry? So we're going to just focus on the relative frequency problem at the moment, which is to say, um, we want to make a data structure that, given an element, estimates how often it appeared. And then to actually identify the heavy hitters in one pass, that's actually going to be left as a homework problem, but it's a relatively fun one. Uh, I don't know. I think you guys will like not trust my definition of fun soon enough, but nonetheless, it's one where you do more algorithm designing than calculations. That's what I kind of meant. Calculations are fun too, but maybe that's a learned thing. Okay. So suppose I did set up this data structure like this. How would I retrieve or estimate? Now, okay, here's element 10. What would you estimate the frequency to be? What would I actually do step by step? Yeah, just go and look at the hash counter and just return that. Okay, so that's going to be our algorithm. So we'll hash in and sort of combine all these counts, um, and then we'll just return the hash, right? Which means the value return is almost definitely some kind of overcount because other things will collide. And the only question is how much, okay, or how often by too much. Okay, so, right. Okay, so when analyzing this, we'll have this kind of notation. Um, so I'm going to let A be this array of counters. So AI would be like the ith counter in that smaller set. I'll use Fi to denote the true kind of absolute frequency of element I. Okay, our goal is to see how close we are to that. And H will be this fixed universal hash function. And M is going to refer to the total length of the stream. And so, for example, the J slot will be summing up all the elements with that hash, their true frequency. Okay, so that's just putting in notation what I think we all agreed with or are in agreement with. Okay. Okay. So here's what I first want to argue. For any of these input elements I, with some probability of error at most 1/2, okay, my estimate is at most like epsilon over 5 times the length of the stream. Right? I'm allowed kind of epsilon m additive error because that's epsilon relative error. Right? So this is saying, oh, okay, half the time it's not a bad estimate for any particular I. So the first inequality, overestimate, is just because, it's just saying it's an overestimate. So that's always the case. So the interesting part is that second inequality. Okay. All right. So here's maybe, I don't think we've done analysis like this before, so this will be good for us. How can we try to analyze this? How can I prove this claim? The claim hopefully makes sense. Ask me questions, of course. But how do I analyze it? Or what's a starting point for many probabilistic analyses? Yeah, let's start with the expectation. Like, it's always good to see if you can understand what the average is. So, what is the expected value of AHI? Right? So, first of all, Fi will always be there, no matter what, plus, and now what? Yeah, so, okay, so I'll put this back in expectation, summing over the expected value of all other elements that have the same hash Fj. Okay? And, okay, I can put linear of expectation and put it inside and just analyze for each person or each item. Okay, so this is a little bit kind of skipping a little bit of notation, but you're going to sum over j that's not equal to I, and you get fj if j collides. Okay, so fi is always there because it always collides with itself. But for all the other items, you'll get fj. Fj is not random. That's part of the input. If they collide, that's random, and randomness we inject. Okay, how do I advance from here? Just overestimate by. Oh, you want to just say this is at most m? Oh, okay. Yeah, let's do one overestimate. Okay, so let's replace one term at a time. So uh, just go a little more slowly for me. What should I write? Okay, so fi plus. Oh, m times the probability? Don't be shy. Let's do it slightly differently. Let's hold off on the replacing fj for the moment. Let's address the probability first. Yeah, it's 1 over k, and k for us is this 10 over epsilon thing. Okay, so fj 1 over w, where w was the width of this array. Okay, now that you have that, you can do a better upper bounding. So what's this whole sum? What's the sum of all the frequencies? M. And then I'm going to plug in for w, m epsilon over 10. Okay, so the expected value is pretty good. In fact, it's even lower by a factor of 2 than our additive error. Okay. Now, this was a statement, a calculation about averages, and that is a statement about something occurring at most half the time. So how do I make this transition? Okay. And so the key, one very important thing is to point out that we're only analyzing how much it's overcounted, which is always non-negative. So Markov's inequality only applies to non-negative things. Okay. So this is m epsilon over 5. Okay. And this is at most, uh, right. So you're going to get 1/2 because the expectation of this quantity is at most m epsilon over 10. So it's saying what are the odds that this non-negative random variable, because it's only overcounts, is at least twice the expectation, and that's your 1/2. Okay? But what's so slick is that we get this nice, oh, it actually works sometimes, using only pairwise independence, because that's all you need to get the expectation. And then with the expectation, you do Markov's, right? So Markov's doesn't need like any of uniform randomness or anything nicer going on here, because it's just something about expectations. Okay, good. So I'm going to make it harder. So we've now shown that for any particular element, our data structure actually works with constant probability. Okay. Now, I want to get all the frequencies, all n, with high probability. Okay, so I want to put this on steroids. Okay, all you've shown is that any particular element is sometimes okay, and now I want to show that all the elements are always okay with very high probability. Okay. All right. Any ideas? Sorry. Oh, can we in particular detect which elements are bad? At some level, have an indicator variable of whether. Oh, well, okay, algorithmically, what would we do? Like, how can I take this, what would I do algorithmically? Or what could I do? We're going to get bullied. Yeah. Okay, we'll just do the same thing over and over again. So, oh, okay, we don't have much time for this, but if I flip a coin, what are the odds that it's tails? And what are the odds that if I flip two, they're both tails? And then what if I did 100 times? What are the odds that they're all tails? I don't know what you guys said, but hopefully you said this. Okay. Alright, so the point is it's dropping rapidly, right? Like super fast. And we're going to leverage this algorithmically. This simple thing that you all know. So we're going to make D copies of this data structure. Okay? So each one is doing this hashing thing. Okay? Now, if I wanted to retrieve an answer for element I, how might I do it with this data structure? I take the average. Take the minimum. The average is often a good answer, but here you can even do better because they're all overestimates, so the minimum is always the best. So you take the minimum. Okay? Now, this will be a bad estimate only if all D of them were bad, which is actually stronger than you would get from the average because it's the min. That's only going to happen with probability 1 over 2 to the D because you're just flipping coins, and how often can you get tails in a row? Okay, it's very simple, right? But the application is very compelling. Okay, so if I choose D to be like 10 log n, right? I'm not worried about log factors. Then suddenly 1 over 2 to the D is like 1 over n to the 10, right? And then finally, if I want to make them all good, as you all said, what's the buzzword? So we can take a union bound. So the probability that some element E is bad, right? So I want to bound the probability of any of these events happening, and I can sum over all of the individual events, which is one particular element being bad. Okay. And so this is at most, there's m elements. Oh no, there's n elements times 1 over n to the 10. So you get 1 over n to the 9. Right? And we're only interested when n's big anyway, so this is like a 0. Okay. So a very simple combination of tricks. So you only end up needing log n over epsilon space, right? And now you're actually able to estimate the relative frequency, that percentage, up to epsilon, additive factor, for all elements ever, with log n over epsilon space, if I treated each counter as constant space, otherwise it'd be like log squared n or log m log n, was polynomially small probability of error. That's what we call high probability. Right? And I threw some new things at you, but ultimately the algorithm is not actually that complicated. Even the hash function itself is just ax plus b. Right? The right thing is kind of these wonderful tricks like identifying this universal hash function is all we need, and then figuring out how to use it. But the concentration, the really strong result just came from, analyzing the average, that wasn't too bad, they collided and stuff. And then saying, it's not going to be more than twice the average too often. And then just flipping coins, right? And saying, it's not going to be wrong all the time. So they're pretty small, simple parts. This algorithm is quite practical. All right, so that's it for today. And so I guess next time we'll do like a real hash table. And in fact, I'll try to present one that's actually used in practice. All right, thank you.